Salutations! Welcome to the fundamental theorem of calculus, part 1. So given that f is continuous on the interval from a to b, and g of x equals the integral from a to x of f of t dt, we know, according to the fundamental theorem of calculus, we know that g prime of x equals f of x. A simple example to demonstrate would be if g of 3 equals the integral from 0 to 3 of f of t dt, then g prime of 3 is simply f of 3.
And another way of saying this is that the derivative of the integral from a to x of f of t dt equals f of x. And a common mistake people will make when getting this derivative is that they will misuse chain rule, so keep your chain rule in mind when you're doing this.
So if you're given the integral from a to x of f of g of t dt, that equals f of g of x times g prime of x.
So we'll start off with a simple example. We have the function q of x equals secant of t cubed on the integral from 7 to x. So to take the derivative of this, we are going to plug the x in the t spot.
Alright, so you're given q of x equals the integral of secant of t cubed plus t from x to 7. So using our properties of integrals, when taking the derivative, you always want the x value to be on top. So using our properties of integrals, you do negative secant t cubed plus t from 7 to x. So when you take the derivative of this, just like you did in the last example, you plug in x. So you have q prime of x equals the negative secant of x cubed plus x.
Hello, now let's look at a problem where we have g of x equals the integral of p squared over p squared plus 1 dt from square root of x to 3.
Oh, sir! The quotient rule!
Don't worry about him, he doesn't know too much. So, similar to our last example, we're going to have to flip our integral and make it a negative as we need that x on the top. So then to take our derivative, we're going to plug the x in for the t's, or in this case the p's, and we have to remember to use our chain rule. So then, once we plug in and simplify it all, clean it up, we got to cancel these square roots and whatnot, we're going to get to here. G prime of x equals negative x over x plus 1 times 1 over 2 square root.
Okay, so this problem says g of x equals the integral from sine of x to x of 1 over the square root of 3 minus t cubed dt. So, you know by the properties of integrals, you can break this up into the integral from sine of x to 0 plus the integral from 0 to x. So, because you always need the x value on top, for the sine of x to 0, you flip it and make it negative. So you get g of x equals negative the integral of 1 over the square root of 3 minus t cubed dt from 0 to sine x plus the integral of 1 over the square root of 3 minus t cubed from 0 to x dt. When you take the derivative, you're simply, as we did in the other problems, you're simply plugging in the sine x for t. So here we get negative 1, which we got the negative from here, negative 1 over the square root of 3 minus sine cubed of x. But don't forget your chain rule, the derivative of sine x is cos x. So you multiply by cos x plus 1 over the square root of 3 minus x cubed, and you simply just plug in this x. And when you simplify it all out, you get g prime of x equals negative cosine x over the square root of 3 minus sine cubed x plus 1 over the square root of 3 minus x cubed. Alright, so a common problem that you might see on the AP exam or on one of Mr. Stone's classical tests would be this. So you're given g of x is the integral from 4 to x of f of t dt, and they ask you to find g prime of negative 2. So you're finding the integral of f of t dt from 4 to negative 2. So when you take an integral, you always need the larger number on top and the smaller number on the bottom. So using your properties of integrals, as we've done in the past several problems, you simply make this negative the integral from -2 to 4.
So, thanks Aashay, now we know we are going from -2 to 4, and we already know the areas between the curves of our shapes. So we're going to take that knowledge, and here we have -2 from here, 2 from here, and -2 from here. So that equals -2, but then we have to multiply that by the negative, which is out in front of our integral here. So we eventually, we'll get 2 from there, and then we eventually get to g prime of -2 equals 2.
Greetings! Welcome to the Fundamental Theorem of Calculus, Part 2. Take it away, David.
So, first we have given that f is continuous on the interval a to b. We come over here to our integral f of x, and that, using the Fundamental Theorem of Calculus, Part 2, we know that the antiderivative of b minus the antiderivative of a is
Equal to the integral of f of x dx from a to b.
yes.
So, say you want to find the integral of x plus 4 dx on the interval from 1 to 4. Using Fundamental Theorem of Calculus Part 2, simply all you do is you integrate x plus 4 dx to get x squared over 2 plus 4x. And you calculate this from 1 to 4. So, first we find f of b. So we plug in 4 for x, and we get 4 squared over 2 plus 16 minus f of a, and in this case a is 1. So minus 1 squared over 2 plus 4 times 1, which is just 4. And when you simplify this, this equals a plus 16 minus 4.5, which gives you a final answer of 19.5. So the integral from 1 to 4 of x plus 4 dx equals 19.5. Ooh la la!
So we'll look at an example. Here we have the integral of cos of t dt from 0 to pi over 2. So we're going to integrate this, which means take the antiderivative, which will be sine of t, still from 0 to pi over 2. And then to solve it, we're going to plug f of b minus f of a. So plug pi over 2 in here, and then 0 in here. And then we know sine of pi over 2 equals 1, and sine of 0 is 0. So we subtract the 2, and we get 1.
So we want to integrate the function x squared dx from -3 to 3. This is a special problem because we know right off the bat that x squared is an even function. So we know that the area under the curve from 0 to 3 is the same as the area under the curve from -3 to 0. So we could rewrite this as 2 times the integral of x squared dx from 0 to 3. And when we integrate x squared dx, we get x cubed over 3. Using the Fundamental Theorem of Calculus Part 2, we could simply plug in 3 and make it 3 cubed over 3 minus, we could plug in 0, which still gives us 0, and then we can multiply that entire thing by 2 to get the integral of x squared dx from -3 to 3. So when you calculate this out, you get 18, and 18 is indeed the area under the curve of x squared from -3 all the way to 3.
This next problem is going to be a doozy.
We want to integrate ln of x over x dx from 1 to e. We know, so first we set u equal to ln of x. We calculate the derivative, and we get du dx equals 1 over x. And when we solve for dx, we get x du equals dx. So you go back to your original, and you know that ln of x equals u, so you can substitute that. And you know dx is the same thing as x du, so you can substitute that. So now, here, the x's cancel out, and we're left with the integral of u du from 1 to e. So when you integrate that, you get u squared over 2 from 1 to e. And you know that u equals ln of x, so this is the same thing as the ln of x squared, quantity squared, over 2 from 1 to e. And using the Fundamental Theorem of Calculus Part 2, you simply just plug in and subtract. you do f of b minus f of a. So you get ln of e is equal to 1. 1 squared is still 1, and 1 squared over 2 is 1/2. And then you subtract it from ln of 1 squared over 2, and ln of 1 is simply 0. So 1/2 minus 0 equals 1/2, and that's your answer.